Hi guys, this is A2 Chemistry, Organic Chemistry, and we are looking at organic synthesis. Question 1. The anti-inflammatory drug ketoprofen can be synthesized from benzene via following 5 steps. And the overall organic synthesis cycle is shown. And let's look at these. We have benzene being converted into an aromatic ketone, which is converted into something to which in step 3, a bromine is added because the molecular formula of T does not have bromine present, which is converted into something in U. And finally, ketoprofen, where COOH is present in place of bromine. So let's make the structures of the missing boxes. So we in U we have the same ketone as was made in step 1, but we will have in place of bromine the presence of CN. The reason being CN would be the only possible substitution here because CN will be hydrolyzed to COOH. And in organic chemistry, the only reaction in which an additional carbon atom is added is when a halogenoalkane is substituted by a CN group or a nitrile group, which is then subjected to acid hydrolysis to produce a carboxylic acid. So this is the structure of molecule U. Now, as for T, we don't have bromine present. So bromine was replaced uh, when the hydrogen was removed from the position at which it is at. Therefore, the product at T would be the same ketone as was produced earlier in step 1, but with the additional side chain present on the benzene ring on the right. So, this is the ketone group, this is the second benzene ring, and this would be the substitute group present, which would undergo free radical substitution with bromine to replace a hydrogen with a bromine atom at the carbon atom that is directly attached to the benzene ring. So we have drawn both the missing structures. Suggest the structures of compounds T and U and draw them in the boxes above, already done. Suggest reagent and conditions for steps 1 to 5. So in step 1, we have a benzene ring with a C double bond O group substituting a hydrogen atom on another benzene molecule. So we would need benzene would be written as C6H5. Then we would need COCl. It would be benzoyl chloride. And the catalyst required for this reaction would be AlCl3. So this way we will end up with the product of step 1. And for step 2, we have a CH3 and a CH2 added onto the benzene ring. So the CH2 would be attached to a Cl, and we would need another molecule of AlCl3 as a catalyst for this reaction. In step 3, we have free radical substitution taking place. So we would be needing Br2 and UV light in order to carry out the free radical substitution. In step 4, we have the Br being replaced by Cn, so we would need either NaCN or KCN along with ethanol, and under the conditions of heat under reflux in order to carry out the nucleophilic substitution, which would substitute the bromide ion with the Cn negative ion. And in step 5, we have acid hydrolysis taking place. So we would need acid plus water plus heat in order to carry out the acid hydrolysis. And this heat would be heat under reflux. So these are all the reagents and conditions for steps 1 to 5. What type of reactions are steps 1 and 5? Step 1 is electrophilic substitution taking place on the benzene molecule. So, electrophilic substitution. And step 5 is the hydrolysis of a nitrile to produce a carboxylic acid. So, we'll call it acid hydrolysis. Step 2 is also electrophilic substitution. Step 3 is free radical substitution, and step 4 is nucleophilic substitution. These are the steps that have not been asked, but we know the mechanism by which the given steps occur. Question 2. The anti-inflammatory drug ibuprofen can be synthesized from benzene via the following 6 steps. So all the steps of the synthetic pathway have been shown. Draw circles around any chiral carbon atom in the above 5 formulae. So in the first one, there are no chiral carbon atoms. In the second one, also we cannot find any chiral carbon atoms. The product of step 3 definitely has a chiral carbon atom, which is the one with the OH and the CN groups attached to it. Then we have a chiral carbon atom in the product of step 6, where the COOH group is present because the carbon atom is bonded to a COOH, a CH3, a hydrogen, and then to the benzene and the rest of the molecule. So these are 4 different groups. So we have got 2 products out of the 5 present, or compounds, because benzene in step 1 is a reactant only, it's not a product. So we've got 2 of the formulae present having chiral carbon atoms on them. Suggest the structure of compounds H and J and draw them in the boxes above. So, in order to see what is happening in step 2, and then we end up with step 3. Step 3 is a cyanohydrin. A cyanohydrin is a molecule with the OH and CN attached to it. So, this is basically a ketone which would be converted into the cyanohydrin, because the carbon to which the OH and CN is attached to 2 other R groups. So it has to be a ketone that undergoes nucleophilic addition. So structure H would be the benzene ring with the substitute group present on it. Then it would be a carbon atom with a double bond O ketone being present on it. So this is structure H. Now, in order to look at structure J, we need to see the product that it forms. So the difference between the reactant of step 4 and the product of step 5 is that our double bond is present and we have a COOH group. So two types of reactions are taking place. One is dehydration, which means removal of water, and the other step is acid hydrolysis of the CN group. So and it is a tertiary alcohol, so it will not undergo oxidation as well. So J could be either of the two structures. Either we could have a double bond present with CN, or we could have the same compound as the reactant of step 4, and in place of CN we can draw COOH. So that is the one I'll be going with. So we have the benzene ring and the rest of the molecule as it is, unchanged. We've got this OH and the CN undergoing acid hydrolysis to produce COOH. So these are the two missing structures from the organic synthetic pathway which we have drawn. Suggest reagents and conditions for steps 1 to 6. So in step 1, we have electrophilic substitution taking place. So the molecule that will undergo electrophilic substitution on benzene would be two CH3 groups attached to a CH group, to which we have a CH2 group attached to benzene. So in place of benzene, we would have a halogen attached here. So the halogen would be chlorine, because of which the catalyst required would be AlCl3. In step 2, we've got CH3 C double bond O added onto the benzene ring, or rather substituted onto the benzene ring. So we would need CH3 COCl, which would be an acyl chloride, and because chlorine is present, the catalyst required would be AlCl3 for this substitution reaction to take place. In step 3, the ketone is being converted into a cyanohydrin. That means we need a nucleophilic substitution reaction taking place. So we would need HCN plus NaCN as a catalyst, and then we would be requiring HCl for acidic conditions in order for the cyanohydrin to form. Next, we have hydrolysis of the cyanohydrin, and that is acid hydrolysis. So we would be needing HCl plus H2O for the hydrolysis to occur, and we would need the conditions of heat under reflux. In step 5, we have dehydration of the alcohol. So OH will be removed from the second carbon atom from the top and hydrogen from the first. So removal of water is taking place. So we can have two conditions for this. Either we can have Al2O3 at 350 degrees Celsius, or we could have concentrated H2SO4 at 170 to 180 degrees Celsius, both of which will carry out dehydration of the alcohol. In step 6, the double bond no longer remains and is converted into a single bond with the carbon atom forming single bonds with hydrogen atoms. So this is hydrogenation taking place, and the conditions for hydrogenation are nickel or platinum as catalyst at 150 to 200 degrees Celsius along with hydrogen gas. And in this way, we have covered all the reagent conditions for steps 1 to 6. Name the mechanism of step 1 and state the type of reaction for step 6. So the mechanism for step 1 is electrophilic substitution of benzene. And in step 6, we have hydrogenation taking place for the alkene group. So hydrogenation. Question 3. Ibuprofen and paracetamol are pain relief drugs. Draw the structure of organic products when ibuprofen and paracetamol react separately with LiLH4. So LiLH4 is a harsh reducing agent. So when ibuprofen is subjected to reaction with LiLH4, the carboxylic acid will be converted into a primary alcohol. And that is the only group that will be affected. So we draw the rest of the molecule as it is. And then we convert the COOH into CH2OH. And since this is a skeletal formula, we will not show the CH2 group. In fact, we will just show the OH group that is attached to the CH2 group. So this is the product with ibuprofen. Now, the product with paracetamol, we have got a phenol group and an amide group. Nothing will happen to the phenol group, so we draw the phenol group as it is, and the amide group will undergo reduction and will be converted into an amine. So we convert the C double bond O into CH2, and that is the product with paracetamol. A student carried out some reactions with solutions of ibuprofen and paracetamol using reagents D and E, and the following results were obtained. A tick means a reaction took place. So D reacted with ibuprofen and not with paracetamol, and E reacted with paracetamol and not with ibuprofen. So the difference between ibuprofen and paracetamol is ibuprofen has a carboxylic acid group and paracetamol has an amide and a phenol group present. So a reagent that only reacts with a carboxylic acid group and not with amide and phenol is sodium carbonate. Sodium carbonate will undergo an acid-base reaction producing CO2 and H2O, and the carboxylic acid group will be converted into a sodium carboxylate group. And E should be something that should react either with phenol or amide. Amide being neutral will not be affected, so we consider the phenol group, and phenol on reaction with aqueous bromine produces a white precipitate. So the reagent would be Br2 aqueous. Give the structure of the organic product formed when reagent D reacts with ibuprofen. So that would be the carboxylic group converting into the sodium carboxylate group. So we draw the rest of the molecule as it is. And the C double bond O group attached to O negative and Na positive. That is the sodium carboxylate portion that is formed upon reaction with sodium carbonate. And the product with paracetamol would be the amide portion and the benzene ring would stay as they are. So NH, C double bond O and CH3, and the OH will also stay as it is, but the positions 2 and 6 when counting from phenol would be bonded by bromine atoms. So hydrogen will be substituted by bromine at these positions, producing a white precipitate. Question 4. Oleocanthal Q is a natural compound found in olive oil. It has antioxidant and anti-inflammatory properties and is thought to have a protective effect against Alzheimer's disease. The structure of Q is given. Q shows optical and cis-trans isomerism. On the structure of Q above, circle the functional group that shows cis-trans isomerism and indicate with an asterisk the chiral carbon atom. So we need to find a double bond. There is only one double bond that belongs to an alkene that shows cis-trans isomerism. So this is it, the one circled in red. And we need to place an asterisk on a chiral carbon atom. So the only carbon atom with four different groups attached to it is the one next to the double bond that has been circled in red, and it will be marked with an asterisk in blue. And we have identified the two different groups which will show optical and cis-trans isomerism in compound Q. Complete the following table to show the structures of the products formed when Q reacts with the three reagents. So the first reagent is excess of bromine. So bromine, and it is aqueous, so it will react with the phenol and the alkene portion of the molecule. So with respect to the phenol portion, we have the OH group attached here. So bromine would be attached on both its adjacent carbon atoms because at the fourth position, there is a substitute group already present. And that substitute group will be drawn as it is because we are going to reach the double bond where electrophilic addition takes place on the benzene, or not the benzene, the alkene molecule, because of which we have bromine atoms attached to both the carbon atoms forming the double bond, and they are now converted into single bond. So one Br here and another Br would be attached here. So two Br attached to the two carbon atoms that had a double bond on them. And the type of reaction with respect to the reaction taking place on the phenol, this is electrophilic substitution. And with respect to the alkene, this is electrophilic addition. Both these types of reactions take place on the same molecule because two different types of organic functional groups are present on them, on it. The next reagent we are going to use is NaBH4, which is a mild reducing agent, which will reduce the ketone groups and the aldehyde groups present, and there is no ketone, only aldehyde groups. So it will reduce the aldehyde groups present into primary alcohols, and it will have no effect on the alkene group, the ester group present in between, and the phenol group present on the left. So both the double bond O's will be converted into single bond OH. So the product would be the benzene ring attached to OH, the phenol portion of the molecule. Then we have the ester portion, which will also be unaffected. Then we have the double bond O at the top being converted into OH. Then we have the double bond at the bottom, double bond O at the bottom being converted into OH as well. So in this way, we have the conversion of both the aldehyde groups into primary alcohols. And this reaction is called reduction because NaBH4 is a reducing agent. The next reagent we are going to use is excess of hot NaOH. Now, since we are using hot NaOH, the ester bond will break and we will have formation of two products. One product would be the one on the left and the other product will be the one on the right side of the ester bond. So the ester bond that's going to break is drawn on the diagram right now, and the product on the left would be the benzene ring with the OH group being converted into O minus and Na plus because phenol is acidic, so it will also react with NaOH, and the single bond O broken away from the ester group will be converted into OH. This is one of the molecules. The second molecule will be O minus Na plus starting from the C double bond O group, and then the rest of the molecule will stay as it is. There will be no further reaction taking place on the remaining molecule. So this is the rest of the molecule. So the only groups affected are the ester group, which undergoes hydrolysis, and the phenol group, which undergoes acid-base reaction to produce salts on each of the two molecules. So the reaction would be called hydrolysis. And if we need to add further detail, this can be called alkaline hydrolysis because the substance used for hydrolysis is NaOH aqueous. When a sample of Q synthesized in a lab was compared to a natural sample from olive oil, it was found that the therapeutic activity of the synthetic sample was lower. Suggest a reason for this. So, naturally occurring Q occurs in only a single optical isomeric form, whereas the synthetic one is produced as a racemic mixture, and a racemic mixture has both optical isomers present in equal quantities. So the one that is naturally occurring will be bringing about the beneficial effect, and half of the synthetic product produced will not be carrying out the beneficial effect. In fact, it will be carrying out or producing harmful side effects. So that is why the therapeutic activity of the synthetic sample is lower than the naturally occurring one. Question 5. Two isomeric aromatic compounds V and W each contain three functional groups, two of which are shown in the table. Complete the table with the other functional groups present in V and W. So we've got a bromo group in both, we've got a benzene or an aryl group in both, and the group that is missing is in V, we've got CONH, which is the amide group, and in W also we've got NH and CO, which is the amide group. So the third group in both the substances V and W is the amide group. Compounds V and W can be synthesized from bromobenzene by the following routes. Okay, so V and W both are the products given. The starting material is bromobenzene, and step 1 has a CH3 group substituting a hydrogen atom on benzene. Step 2 forms R, which reacts with PCl5 to produce S, which produces an amide group on reaction with an amine in place of CH3. So, if an amide group is formed in place of an amine, that means the group that would react with CH3NH2 would be an acyl chloride group. So, the molecule of S would be the benzene ring with bromine present on one end, and the C double bond O group bonded to a chlorine atom. This would be the acyl chloride that would react with CH3NH2, forming the amide, which is compound V. Now, since this is the COCl group present here, and the starting material was CH3 at this position, that and this product R reacted with PCl5, that means the same ca- acyl group will now be present in the form of a carboxylic group, because the carboxylic group would react with PCl5 and will be converted into an acyl chloride. So this would be the carboxylic group, and the bromine molecule will be present as it is. So these are the structures R and S as identified from the organic synthetic pathway given. Next, we would look at the step 3 and step 4 to produce W. So step 3 has Br present as it is, and it goes on till the end till product W, whereas in step 4 we have something that would react with CH3COCl, which is an acyl chloride. Now since CH3COCl is an acyl chloride and the final product is an amide, that means the product T would be an amine. So in order for product T to be an amine, we would have the benzene ring and the bromine atom placed in their positions as they are, and the NH would be converted into NH2, and this NH2 would be formed from NO2 when NO2 groups undergoes reduction. So in this way, we have completed the empty boxes R, S, and T with their appropriate organic molecules. Suggest reagents for each of the steps 1 to 4. So step 1 is CH3 substituting hydrogen on benzene. So that would mean that CH3Cl would react with benzene in the presence of the catalyst AlCl3. And in step 2, the CH3 group is converted into COOH, which is oxidation. So we would need acidified KMnO4 and heat in order for this reaction to occur. In step 3, we have nitration of bromobenzene taking place. Nitration occurs in the presence of HNO3 with the catalyst H2SO4 and temperature of 50 to 55 degrees Celsius for nitration of benzene. But since this is bromobenzene, warming would also be sufficient for this reaction to occur. So instead of 50 to 55, we would write warm. Next, step 4. Step 4 is the reduction of the nitro group into an amine group. So the reduction of nitro group takes place in the very specific conditions of placing a tin metal along with concentrated HCl. Reduce the structure of R, S, and T and draw their structural formula in the boxes. Already done. Draw the structures of the two organic products from the reaction of V and W with LiLH4. So LiLH4 is a harsh reducing agent which would reduce the amide bonds or amide group into amines. Now the difference between structures V and W is that V is bonded to the benzene ring is bonded to the C double bond O group and then NH, and in W the benzene ring is bonded to NH and then C double bond O. So the product would be the benzene ring attached to bromine, which is common in both the products. Then in V, we would have the CO group, C double bond O group being reduced into CH2, the NH group staying as it is, and then it is bonded to CH3. And in case of W, the positions of NH and CH2 would be changed, and we would have NH present first, then CH2, and then we have CH3. So the CH2 groups in both positions have been formed by reduction of the amide group into the amine. So the C double bond O group was removed and replaced with CH2. Name the type of reaction occurring between LiLH4 and V and W. So this reaction is called reduction. V and W can be hydrolyzed using hot HCl. Draw the structure of the two organic products of the hydrolysis of W. So we are using HCl. So we have the benzene ring with bromine bonded to NH2, but this is not the final product. And the other one would be the C double bond O group attached to OH and CH3 on the other end. This is a final product. So the reason why I said this is not the final product is because the NH2 group makes phenylamine basic in nature and the reaction is with an acid. So the acid would react with the base as a secondary reaction and this will be converted into NH3 positive and Cl negative. It will be converted into an ionic salt. So this is the final product of this reaction because the hydrolysis that was occurring was in the presence of the acid and the product formed was basic in nature. So the basic product reacts with the acid present as a secondary reaction to produce an ionic salt. The products formed from the hydrolysis of W are soluble in aqueous acid, whereas a precipitate X is formed on hydrolyzing V. Draw the structure of compound X. So, precipitate X is formed by hydrolyzing V. So, the precipitate X would be the benzoic acid containing bromine because in place of NH, CO would be present on the benzene molecule. So the product form would be the benzene ring with the Br atom on one end and the COOH group on the other end. Suggest why X is insoluble in water. It has got a large non-polar alkyl group present which prevents it from dissolving even after the hydrogen bonding is formed between the RCOOH group and H2O. So the carboxyl group will form a hydrogen bond with water, but since the rest of the molecule is much larger and is non-polar, the molecule will still not dissolve in water. Question 6. The compound advantame is a sweetener that tastes approximately 25,000 times sweeter than sucrose, and the structure of advantame is given. Advantame is optically active. On the diagram of advantame, circle all the chiral carbon atoms. So, chiral carbon atoms are carbon atoms attached to four different groups via single covalent bonding. So, if we start from left to right, the first carbon atom that we encounter is the carbon atom between the NH and the CO group. This is the first chiral carbon atom present in advantame. And then we move on. The other chiral carbon atom is next to the amide NH and the ester C double bond O group. So this would be the second chiral carbon atom present in advantame. And as we move further, no other chiral carbon atoms are present. So in total, two chiral carbon atoms are present in a molecule of advantame. The decomposition of advantame produces three molecules J, K, and L. The RO group in advantame is unreactive. Okay, suggest a possible reaction condition for this decomposition. So the decomposition of advantame produces a carboxylic acid and an amine. So basically, we have the CONH group being broken and then the ester group being broken. So the groups that are broken will be marked with the line passing through them. So this is one of the groups that is broken, producing molecule J on the left, and the other one that is broken produces molecule K given, which means the remaining molecule is CH3OH. That is the third molecule L, which we have been asked to draw the structure of later in the question. Suggest possible reagent and condition for this decomposition. This decomposition can take place in the presence of acid, water, and heat under reflux. So this is basically acid hydrolysis. Name the type of reaction occurring. Acid hydrolysis. And draw the structure of L in the box above, already drawn. Excess bromine was added dropwise to a solution of J until the bromine was in excess. Aqueous bromine was added dropwise. So state what you would observe. For this, we will need to look at the structure of J. Okay, on this molecule of J, when bromine would be added, so we don't have any alkene groups present. However, we do have an OH group present attached to benzene, which makes it a phenol. So on a phenol molecule, we would have substitution of bromine taking place at 2, 4, and 6 positions. So if we count from the OH group clockwise, the second position is occupied by the OR or RO group. The third position will not be substituted. The fourth position will be substituted by bromine, and fifth is already occupied, and the sixth position will be substituted by a bromine atom. So observation would be formation of a white precipitate, because when bromine adds or rather substitutes onto the phenol molecule, the precipitate formed is white in color, and the brown color of aqueous bromine discharges. So we will write the brown color of aqueous bromine discharges and a white precipitate forms. J has the molecular formula C14H19O6N. Use this formula to write an equation for the reaction of an excess aqueous sodium hydroxide with one molecule of J. So we would have C14H19O6 and N reacting with NaOH. The number of molecules of NaOH that would react would be seen by looking at the structure of J again. So on this molecule of J, we have one phenol group and two carboxyl groups, in which the OH groups will be replaced by O minus Na plus. So in other words, we have removal of three hydrogen and addition of three sodium. So in the equation that we will make, we will decrease three hydrogen atoms from the molecular formula and add three sodium ions in that formula. So this equation would become the molecular formula of J plus 3 moles of NaOH producing C14H19 minus 3 is 16, O6, N and Na3. These will be added onto the OH groups, and removal of hydrogen from the OH groups result in the formation of 3 moles of H2O, because if sodium from NaOH is added onto J, then the OH groups remain and the hydrogen removed from J would react with those OH negative ions producing 3 moles of water. So this is the equation for the reaction of J with an excess of aqueous sodium hydroxide. State what you would observe when an excess of aqueous bromine is added to a solution of K. So for this, we need to look at the structure of K. In the structure of K, we have a benzene ring attached to a CH2 group, to which we have a CHNH2 group attached, and which is also attached to a COOH. So we've got an amine and a carboxylic group attached to the same carbon atom. So K is in fact an amino acid. So we don't have a phenol group or an alkene group. So addition of aqueous bromine will have no effect to the molecule of K. No reaction would take place. That means it would give no observation. So state what you would observe when an excess of aqueous bromine is added to a solution of K. There would be no visible change observed. So no visible change observed. K can be polymerized. Draw the structure of the polymer showing two repeat units. The linkage between the monomer units should be fully displayed. So this is an amino acid in which we've got the NH2 group on one side and the COOH group on the other side of the same carbon atom, with a hydrogen attached to it and a CH2 and benzene attached to it as well. So the product having two repeat units, or the polymer having two repeat units, would be NH on one side with CH, CH2 and then benzene ring. So CH2 with benzene on the third side, and on the fourth side we've got the C double bond O group attached to the NH group of another molecule of K, attached to the CH group on one side, the CH2 and benzene ring on the other side, and attached to the C double bond O group on the fourth position. And since we are drawing repeat units, we will draw a bracket at the starting and the ending position of the two repeat units, and it says the linkage between the monomer units should be fully displayed. So this is the fully displayed linkage between the two monomer units, which is referred to, since it is an amino acid forming a polymer, which is referred to as a peptide, or in other words, an amide bond or linkage. So this has been fully displayed for clarity, and that is the two repeat units of molecule K. after it undergoes condensation polymerization.